in chapter 14, what we're going to be doing is looking at functions that have two variables. So what this means is when you look at something, sometimes it's not just determined by one thing, it might be determined by two things. So for example, cost is one that has a lot of variables. So the total cost it takes to produce an item could be the cost of labor as well as the actual cost of the item plus the cost of the building that you're producing it in, things like that. So what we're going to start with is finding the domain, and we're just going to review finding the domain when you just have one variable, and that's going to help us find the domain when we have multiple variables. So first off, you want to start with all real numbers and then start removing values. So if you see a square root, then whatever you see under that square root has to be greater than or equal to 0. So you're going to set that to be greater than or equal to 0. The reason is that we only want positive values. If you take the square root of a negative, you're going to get an imaginary number, which is not something that we want. So for example here, if we want to find the domain of this function, we have a square root. So we're going to take the stuff under the square root and say, okay, that needs to be greater than or equal to 0. And what that tells us is that x has to be any number greater than or equal to 2. And that would be our domain. Now, if you don't see a square root, then what we need to look at is if you have a denominator. So do you have an x in the bottom of a fraction? If you do, then what we need is to make sure that we don't break any math rules, we need the thing underneath that to not equal 0. Okay, remember, you just can't divide by 0. So for example, if we want to find the domain of this function, g of x, okay, we don't care about the top, we only care about the bottom not equaling 0. So we want x minus 4 to not equal 0, which means that x can't equal 4. All right, so let's take a look at this when we have multiple variables. So we're going to do the same thing. So when we look at the function of z of x, comma y, and it equals on the top 4x squared minus 5y, and on the bottom it's 7x minus 3y, here's what we're going to do. First we're going to start with all real numbers. Then we're going to look for a square root, which we don't have, and the next thing is that we're going to look at the denominator. So if we look at the denominator, remember, what do we want the denominator to do in order to not break any math rules? We just don't want that to equal 0. And that's it, you're done. We just don't want the denominator to equal 0. So we're finished. Now for the next one, we want to find the domain of q, comma p1, comma p2, so we have two variables, p1 and p2, and that equals the square root of p1 minus 4 plus 5p2. So again, we're going to look and see, do we have a square root? We do have a square root. And remember, we want whatever's underneath the square root to be greater than or equal to 0, which means p sub 1 needs to be greater than or equal to 4. Now we're not done. What we need to do is that we also need to talk about p2. Now if we look at p2, is there any square root? Nope. Is there any denominator? No. So what that means is that p2 can be all real numbers. So this would be our answer for the domain, is that p1 has to be a number greater than or equal to 4, and p2 can be any number we want it to be. All right, now the last example is actually evaluating a function with two variables. So we're going to use the previous one. So we're going to have the square root of p1 minus 4 plus 5p2, and we want to evaluate it if p1 equals 7 and p2 equals 2. This is exactly what you think it would be. You're going to plug those values in for their variables. So we're going to plug 7 in for p1, 2 in for p2, and what we're going to get is the square root of 7 minus 4 plus 5 times 2. So let's see, 7 minus 4 is going to give us the square root of 3 plus, and that's going to be 10. So that would be our answer right there. In the next video, we're going to be looking at taking the derivative of multivariable functions and then doing an application.